Hi, I'm Michelle Lamb, and I'll be sharing Concept Induction, our work on analyzing unstructured text with high-level concepts using LLooM. This work was done with my amazing collaborators at the Stanford HCI Group and the University of Washington Interactive Data Lab. Let's follow a few HCI researchers in the wild. Researchers in one group are exploring how LLMs display empathy in user interactions. From hundreds of results, a select number of trends make it to their paper, like that LLMs show empathy towards perpetrators of hate. Researchers in another group are exploring parallels between the LLM chaining and crowdsourcing literature. From over 100 papers, they report a theme of diverse responses gathered using parallel, iterative, or debate-based workflows. Another group of researchers is analyzing the impact of politics on social media. From hundreds of posts, they find some salient themes, like posts that only partially present political facts based on party affiliation. As you might be noticing, researchers often run into a similar problem. They need to know what are recurring themes in these texts. This problem comes up even as they're teaching courses, reviewing student applications, and giving talks. And chances are you also run into this challenge. How do we get meaningful signals from messy text data? This is a critical foundational step before we can even make a decision about what problems to study, let alone what models or systems to build. Going back to those examples, isn't this problem solved? Well, to arrive at those findings, researchers use manual categorization, which allows for a rich understanding and is the gold standard for in-depth textual analysis. Unfortunately, manual approaches don't scale up easily. Tools are helpful to sift through massive datasets. On the other hand, automated algorithms like topic modeling are popular and make large-scale analyses feasible. But they produce low-level text signals like keywords. These are a far cry from the nuanced themes that researchers developed through careful manual analysis. To bridge this gap, we introduce concept induction, the task of synthesizing high-level concepts from unstructured text, where we define concepts as natural language descriptions defined by explicit inclusion criteria. For example, concept induction will produce outputs like government accountability and social justice focus, and each concept is defined by detailed criteria. In contrast to existing methods, concept induction aids interpretation, allowing users to focus less on understanding concepts and more on applying and extending concepts to make sense of data. To achieve this vision, we develop a concept induction algorithm called LLooM, which draws on the ability of large language models to generalize from examples. LLooM samples extracted text and iteratively synthesizes proposed concepts of increasing generality to produce high-level concepts. I'll walk through the core operators of the LLooM algorithm. The synthesize operator is the most important one. It prompts the LLM to generalize from provided examples to create concept descriptions and criteria in natural language. If we run this just directly on input documents, we tend to end up with broad, generic concepts, as we'll see when we get to the evaluation. To address these issues, we included two operators that go before the synthesize operator to aid both data size and concept quality. The distill operator scales down the input data while preserving salient details, first through a filter step and then with a summarize step. The filter step performs extractive summarization to pull out quotes from the input text. The summarize step generates abstractive summaries in the form of short bullet points. Then these distilled bullet points are detached from their original examples and reclustered together to generate cross-cutting groupings. In our implementation, we use OpenAI embeddings and HDBScan to perform this pre-clustering step, which increases the likelihood that more thematically similar text spans are kept together. Finally, there are a few additional operators that allow for greater control. The seed operator allows the user to specify a seed term that captures an area of interest. For example, they can focus on social issues in a political dataset or displays of emotion in a conversations dataset. This seed term is added onto the distill and synthesize operators to steer the way that text is summarized and the kinds of concepts that are proposed. Then the score operator allows us to find concept matches in the input data. After concepts have been generated, the score operator applies the concept inclusion criteria against all documents in the dataset to estimate how well each document matches the concept, including rationale and relevant highlighted quotes. This operator bolsters reliability and gives us a sense of concept prevalence. Then the loop operator can be used to execute multiple iterations of the algorithm. This operator carries out logic to revise the inputs to the next iteration of the pipeline, based on how well current concepts cover the documents. Those that don't match any concepts or that only match common generic concepts will be run through concept induction again. In summary, the key components are the distill, cluster, and synthesize operators, and the seed and loop operators allow users to steer or iterate on concepts. After this concept generation phase, We can run this concept scoring process that I described earlier to classify the entire dataset. And we can visualize our dataset in terms of the generated concepts in the LLooM workbench, a mixed initiative text analysis tool. The LLooM algorithm operators and workbench are available as an open source Python package designed for use in computational notebooks. Let's see how the LLooM workbench was helpful for a domain expert in one of our case studies. Here, to make sense of political social media posts that might drive partisan animosity. The workbench shows the concept induction results. Each row is a high-level concept synthesized by the LLooM algorithm. To explore a concept like political party positions, we can click on a row. In addition to the concept name, LLooM allows the analyst to inspect the generated inclusion criteria, which captures the positions or actions of political parties. LLooM also shows the sub-concepts and examples that led to the concept, which here appear to cover partisan stances on issues like healthcare. In the matrix view on the left, LLooM allows the analyst to slice the data by manual partisan animosity scores, here from low to high partisan animosity. The circles indicate higher prevalence for high partisan animosity examples, so the analyst explores further. LLooM surfaces examples that match the political party positions concept, and there are many posts that are written from one party's perspective and attacking the other party's stance. This reminds the analyst of a construct of social distrust they'd seen in a political science paper, so they're curious to see whether this applies to the data. LLooM allows the analyst to create their own concepts and apply them to data. They add a new concept based on this social distrust measure, and in 10 to 20 seconds, it's added into the LLooM workbench. The analyst finds that this concept indeed aligns with moderately high partisan animosity scores, but there might be factors that play a stronger role in the most extreme cases of partisan animosity. Ideas like social distrust can be hard to pick up on, but LLooM extracts relevant examples that display distrust, even though the text doesn't explicitly mention distrust. Now that you have a sense for how LLooM works, I'll walk through 3 different evaluations we ran to answer different questions. For our technical evaluation, we wanted to understand how well LLooM concepts aligned with human topic annotations. It's important to note that there isn't a real ground truth here. Even human annotations might not capture all of the valid concepts in a dataset based on a given analyst's interests. However, this provides a reference point and allows us to compare against other approaches. We ran evaluations on both real-world topic modeling benchmark datasets as well as synthetic datasets. While real-world datasets are the best for external validity, in our scenario, there are risks that LLMs may have memorized the labels from the pre-training data. Additionally, these datasets have static characteristics, which make it challenging to study how changes to the text might impact system performance. We thus add synthetic datasets that address these gaps and let us experimentally vary document characteristics. Our paper discusses more details on the datasets and our synthetic data generation method. We use a Congressional Bill Summaries dataset and a Wikipedia articles dataset for the real-world datasets, which have manual ground truth topic annotations. And we generate synthetic datasets that vary in length, concept prevalence, and that both contain overarching generic themes as well as specific nuanced concepts. These are ground truth concepts that we've seeded in the dataset, and this specificity dimension allows us to separate out how well LLooM works at surfacing generic topics versus specific ideas that are not always captured by topic model. For our baselines, we compare against per topic, representing the state of the art in cluster-based topic modeling, and then we compare against base LLMs, GPT-4 that has a smaller context window, and GPT-4 Turbo that has a larger context window to fit documents. For parity, we prompt the base models with the same LLooM synthesized prompt. We of course compare these against LLooM, and we evaluate these methods based on concept coverage, the proportion of ground truth concepts that a method successfully recovers. On the Bills dataset, LLooM significantly outperforms baseline methods, including GPT-4 Turbo. Notably, this dataset is less likely to have occurred in the GPT training data, while the Wiki dataset is potentially in the training data. And when we look there, we see that indeed performance on both GPT baselines jumps up, suggesting that performance can be inflated on datasets familiar to the model. For the synthetic datasets, looking at the generic concepts, which are more akin to the topics in the benchmark dataset, we find that LLooM achieves a very high concept coverage, as does GPT-4 Turbo. But when we look at specific concepts, the more nuanced ideas in text, LLooM significantly exceeds all baselines. And this difference comes through qualitatively. Per topic on one end is a different sort of output that is necessarily vague since it produces keywords. GPT-4 can recover ground truth topics, but it has a failure mode of conflating multiple. GPT-4 Turbo improves upon this and matches the generic concepts very well. However, LLooM provides both generic concepts and specific concepts, as highlighted in blue. It captures both broad, holistic themes, as well as the specific behaviors or patterns that are occurring within those themes. Our technical evaluation finds that LLooM produces high-quality concepts. How does LLooM work in different domains beyond benchmark datasets? We explored 4 different LLooM analysis scenarios. Here, I'll give a preview of 2 of them: content moderation and AI ethics statements. The content moderation scenario deals with a dataset of toxic social media posts related to women and feminism. With LLooM, I get concepts like gender norms critique and workplace gender issues, and we see that misogyny, stereotypes, and gender norms are widespread in this dataset, while empowerment is much less prevalent but present. I'm interested in the use of metaphors for toxic content, so I can provide a seed of metaphorical language. Now we see concepts highlighting metaphors that are used to express emotions, reinforce gender stereotypes, and discuss patriarchy. Some of the summaries bring up how women are objectified with these metaphors. The NeurIPS scenario looks at a dataset of broader impact statements from 2020 NeurIPS submissions. LLooM surfaces concepts like ethical considerations and robustness and security. Data privacy and energy and efficiency are much less prevalent compared to ethical considerations. When we dive into the types of negative outcomes that authors describe using a seed, we find that bias and fairness and security and attacks are the most common. However, there are also issues related to environmental impact and job displacement that are important but less frequently highlighted. Then we can look at mitigation strategies authors propose with a different seed. Authors commonly discuss ideas like improving robustness and mitigating bias, perhaps reflecting a greater emphasis on system performance as opposed to other possible negative societal and human impacts. These scenarios give us a glimpse into how LLooM concepts can illuminate recurring themes in a dataset. Going beyond standalone concept generation tasks, how might LLooM aid realistic data analysis tasks? We specifically chose to run first-use sessions with expert data analysts who had already authored a publication on a dataset. These analysts are a discerning and critical audience who already hold a strong understanding of the dataset, so they can provide expert feedback on the utility of LLooM outputs. We ran 1-hour sessions where, for the given dataset, we had an analysis task using BERT topic outputs, a task using LLooM Workbench, and a concluding interview. As a quick overview, we had the experts rate each BERT topic and LLooM output in terms of whether it was helpful, interpretable, and unique. And LLooM concepts were consistently rated as more helpful and were more unique, and were universally viewed as interpretable. Where things got a little bit more interesting is when we walked through the analyst's experience as they were analyzing data. For the sake of time, I'll cover one expert's experience in depth as it's illustrative of both case studies. When analyzing the BERT topic results, the expert spent most of their time just making sense of the vague and overlapping topics. What does oil, gas, energy, strategic mean? What's the difference between House, Republicans, Democrat, and Rep, Congress, Great? This required going back and forth between these keywords and the raw examples themselves. By contrast, when using the LLooM Workbench, users spent their time primarily exploring data through the lens of concepts. They didn't need to go and spend time focusing on understanding the concepts themselves. For example, the analysts quickly reviewed trends that they had anticipated, like that political commentary and explicit discussions of government were tied to high partisan animosity, and that bipartisan concepts like government accountability and public health displayed low partisan animosity. However, they were also able to quickly hone in on concepts that violated their expectations. For example, a relatively benign-looking concept of political party positions had high partisan animosity. Inspecting further, they realized that many posts were making attacks on out-party stances, not just talking about their own party positions, so it seemed like a noteworthy trend of divisive discourse. In cases like these where the analysts noticed nascent patterns, they were able to investigate further. In the policy-related concept, they saw posts that were overly dramatizing outcomes of policy, like immigration laws and health programs. They created a custom crisis concept and were able to isolate more posts like this that were mentioning crisis resulting from a policy implementation. And they indeed found that these were high partisan animosity posts. Finally, analysts were also able to draw on relevant prior knowledge to form theories as they explored data. For example, the analyst was reminded of a construct from political science literature and authored a social distrust concept to find relevant content. LLooM allows analysts to explore data in terms of concepts rather than sifting through model parameters. LLooM can amplify theory-driven data analysis by allowing analysts to draw out high-level concepts, weave together connections, and form a narrative tapestry supported by input data.